All right, guys. Oh, it's not working. All right, let's get started. A few reminders. Exam 1 is a week from today, so don't forget, right? Remember, it's closed notes, but you're allowed a cheat sheet. And it's going to cover everything from the beginning of the semester until now. So yeah, essentially symmetric encryption, mostly block cipher. Okay, so today I'll finish the DES algorithm. We were talking about the Feistel network. So we'll finish that up. Yeah, and I also have some slides. So I'll go over those slides to kind of finish that up as well. But yeah, that's the plan. Are there any questions before I get started? Yeah, go ahead.
Does the cheat sheet have to be manually written or can it be typed?
You can type it.
Okay.
You can write whatever you want on it. Okay. All right. So let's go ahead. And yeah, 350. So I have a few slides, and hopefully you've been looking at these. They just kind of summarize some of the concepts. There's a few graphs. So just a few things to talk about. And kind of this is sort of the end of symmetric encryption. And we're moving into, well, this is the end of the first third in the exam. And we're moving into the next topic, which is asymmetric encryption. And that is like really nice, I think, in my opinion. It's like very nice. If you like XOR, and you like symmetric encryption, you will like RSA way much more. Very interesting, right? Almost like magic, but it's math. All right. So, but yeah, so it's going to be pretty interesting. And then, of course, these topics don't go away because we'll be using both symmetric and asymmetric encryption together to start to build more complex solutions. Okay. So that definitely. So let's take a look. So I think, this was the first module. Whoops. This was the first module, and I know I've done these slides. And then I think I have 2 more sets of slides to go through. There's no slides here. And I think there's no slides here either. Yeah. So it should be in the next one, hash function. There it is. So we have 1 set of slides. We'll just go over these, a few additional, kind of like a review or a summary before the exam. And I'm going to lay the groundwork for RSA and asymmetric encryption. Okay, so let's go download this one. Okay, and then we can get the other one in a second. It should be starting. All right. See that? So I'm going to share the screen. All right, so a few things to remember. Okay, a few things to remember. Remember the principles, right? There will be some questions on the exam about the principles. So is this integrity? Is this authentication? Is this non-repudiation? Is this confidentiality? All right, so you can expect questions like that. 1 or 2 questions. Symmetric encryption. So we've talked about this for about 4 or 5 weeks. It's the universal technique for providing confidentiality, remember. And this is what you use today. Like every day, whenever you want confidentiality, you're using some kind of symmetric encryption. So confidentiality for transmitted or stored data. Also referred to as conventional encryption or single key encryption. And remember that, we have those keys that have to be shared securely. So 2 requirements for secure use. Needs a strong encryption algorithm, such as AES, for instance. We've talked about DES. We're currently talking about DES. And we know that one is insecure, although it can still be used because it was broken via brute force, right? So there is a delay in how quickly you can get the key. Sender and receiver must have obtained copies of the secret key in a secure fashion and must keep the key secure, right? So this is the problem that we've been having all semester how to share that key. So that's where today I'm going to give some of the ideas, not so much the math or anything like that, but just the general concepts, and we'll go from there. Okay, so we've done these graphs before. So simplified model of symmetric encryption, as you know. So we have a plain text message that goes in. Yes, you can see that there. Plain text goes into some kind of an encryption algorithm, such as DES, and there's going to be a secret key that has to be shared. So then we know that the encryption algorithm takes the key and the plain text to produce the cipher. On the other end, we need to have a decryption algorithm. It's the reverse of the encryption. And we've been dealing with this problem, right, all semester. Whatever you do forward, you have to do in reverse. And that can be complicated. And then that gives us the plain text message. So attacking symmetric encryption, all right? So that's, like the fun part, right? Breaking these things. So essentially, we've talked about this a little bit. We did the first substitution cipher. You guys saw that there was a pattern in that. Even though it's hard to implement, it was highly insecure. That's called cryptanalytics, right? And we're going to learn in the context of RSA how to break RSA. I mean, in theory, although it hasn't been broken yet for a key of a sufficient size, right? This is very difficult. There's also quantum computers now, right? That's Shor's algorithm, and that also breaks RSA, but it requires a quantum computer, which probably does not exist currently, right? So, but yeah, cryptanalytics exploits the characteristics of the algorithm to attempt to deduce a specific plain text or the key being used. Obviously, one thing you all hear about AI. So obviously, I should say probably there's a lot of papers on using AI to break cryptography, no doubt. But the problem with that is, so AI, machine learning, is about patterns. What have we learned about cryptography? Cryptography is about randomness. Do you see that? That's a big gap, right? So that's why if it's enough, if it's very random, then it should have no patterns. So how is machine learning going to break it? Do you see that? So, but you never know, right? So you never know. And so that's why these are interesting areas to look at. All right. But anyway, so that's kind of the thought there. So, um, yeah, cryptanalytics, very, very nice, very interesting. Exploits the characteristics of the algorithm to attempt to deduce specific plain text or the key being used. If successful, all future and past messages encrypted with that key are compromised. So this is actually a very interesting thing that I don't know if you've ever thought about this, but this is a reality for all of you, for all of us, right? So you've been using the internet since you were probably in high school or something like that, right? So think about how much data you've been on bulletin boards, Gmail, all that stuff, right? And whenever we use those services, we're told that it's all encrypted, and it's true. But it is also true that there's some entities out there that have scraped all that data. So everything about that you've ever done digitally, even though it was encrypted, is somewhere stored. Someone has collected it. It is currently encrypted, so they can't access it. But in 15 or 20 years, if there's a quantum computer, they will break that cipher. So all that you've done, they'll have access to. And this is true, right? So that's something that will happen because people have, it's not like that data is destroyed, it has been stored. And so all that it requires is a powerful enough algorithm to break it, which we don't have today. But think about, all the secrets of governments, right? Of everything that they've done. They assumed, they never thought of it, that maybe in the 60s and the 70s, they were like, okay, we're encrypting it, so we're good. But they never thought that, no, that data is being collected and someday something could break all that. And then you get a lot of information that's really valuable, right? So you probably, a lot of governments today are trying to change everything, right? They have to redo anything that was a secret that works well because someday it'll be known. But anyway, that's a true a thing people are worried about that is very true. All right, so that's cryptanalytics. Brute force, of course, you guys know that one. That's a much more less elegant approach. It worked. That's how DES was broken. A lot of things were broken like this, but it takes time and a lot of computing power, right? So that's why you need, smarter algorithms, etc. So brute force is just, trying all the possible things until you get a hit, and that's not very efficient. Machine learning, for instance, uses certain techniques so it doesn't have to try every possible thing. It tries one, gets some feedback about that, and then it uses that information to make a decision for the next thing it's gonna, look at. Quantum computers apparently can do a lot of things in parallel, so they can do the brute force, but many, many times in parallel. So it's much faster, and that's in theory. But anyway, so brute force is the other one. Try all possible keys on some cipher text until an intelligible translation into plain text is obtained, or something like that. So here's an example, a table of how long it takes to break a key. So the bigger the key, the longer it can take because of so many permutations, right? So you've seen this in your math classes. So a key size of 32 might take 2 milliseconds on a very powerful computer, but one of 168 will take how many years that is. So by that time, the universe may have ended, right? And so that's kind of the idea. So it takes that, but that's brute force, right? So that's why you want to use other algorithms that might be better. Okay. All right. So another topic we've discussed, as I said, is we're currently in the middle of DES. And then there's AES. Also, we'll talk briefly about it. AES, I'll try to give you like a very simple Python example a little later. But definitely we'll finish DES today. And so because I do want to move on to RSA and asymmetric encryption. But two of the most important techniques in symmetric encryption are DES and AES. Remember, you understand how it works now, right? Inside is just moving bits around, XORing, things like that. So you should understand that basic idea. These are frameworks essentially, and there might be many implementations of these frameworks, right? Blowfish or whatever they're called. They come with a name, but essentially they're the same thing, same underlying framework. So there's DES, the data encryption standard, that was broken in the 90s. AES, the advanced encryption standard, and they are both block encryption algorithms, as we have seen. Okay, some characteristics. There's also triple DES. I think I gave that anecdote. Essentially, the moment they broke DES, they're like, okay, it has been broken, but it takes a while to break it. So therefore, let's just create an algorithm that takes longer, and that way, we have a little bit more time before we change the key, etc. So you have DES, plain text block size 64, and you can see AES is 128. Ciphertext is 64 to 128, and then the key sizes can be bigger. Remember, when we have a key one of the simplest solution is we use that key to generate a sequence of other keys, and those keys can be of any other size, right? So that's a simple solution. But yeah, that's the idea. So these are the three popular symmetric encryption algorithms. So the data encryption standard, the most widely used encryption scheme, referred to as data encryption algorithm, uses 64-bit plain text blocks and 56-bit key to produce a 64-bit ciphertext block. So if you remember, n bits to n bits, right? So we talked about that a lot. Strength concerns about the algorithm. DES is the most studied encryption algorithm in existence. So remember, there's no security through obscurity. Instead, we study the algorithms, right? And in fact, you have competitions or you have conferences where you try to break these every year. There's a very famous conference called the RSA conference, right? So what do you think you're trying to do there? Break RSA. All right. Yeah, so you can see there, it was announced that in July 1998, DES had been broken via brute force. Here's a nice little chart of the relationship between the key, the number of bits in the key, and the number of years it would take to break the algorithm. So you can see it's kind of linear relationship, and yeah, that's why they keep increasing the keys. Triple DES. So just briefly, it repeats, and I'll show something a little later. It repeats the basic DES algorithm 3 times using either 2 or 3 unique keys. So that's the other point that's actually, I forgot to mention, it's not the same key. So think about it. If you break one key, well, then you have to break the other key, and then you have to break the third key, right? So this is a little bit similar to the scavenger hunt we'll have around week 12, right? Where I will encrypt a secret message with everything that we've learned in this class. And so you guys will have to, it's like you break one and you get a key, then you'll break another thing and you get another key, but you'll need all 3 keys to get the final message or something like that. All right. It was first standardized for use in financial applications. Yeah, so have a higher key would overcome the vulnerability to brute force attack. Okay, so that's the key aspect. But the underlying encryption algorithm is the same as in DES, and you guys already know it. We'll do a simple Feistel implementation later also, so using the CBC algorithm. So you'll see that actually implementing it is not as difficult. So the Feistel network looks confusing and hard, but actually the code implementation is pretty simple. And so you can, but we'll look at that after the exam. Yeah, drawbacks. Obviously, the algorithm is sluggish in software. You're doing it 3 times. It just increased the amount of time it would take, right? So much slower. AES, the advanced encryption standard. So this one's a bit, better. So essentially, at that point in time, early 2000s, late 1997, they needed a replacement for triple DES because triple DES was not reasonable for long-term use. It's kind of a hack, right? Not intended for that. NIST, you guys have heard of that, National Institute of Standards. So they govern these kinds of things. They're the ones I think also that are publishing the quantum algorithms and everything for cryptography. So you can look them up there. So it called for proposals for a new advanced encryption standard, and this is kind of what they wanted, right? So they said should have a security strength equal to or better than triple DES, significantly improved efficiency. Remember that in crypto, efficiency is key, right? If you're downloading a whole movie, right, you can't take 30 minutes to download that movie because of the encryption process. So it needed to have good efficiency. They wanted it to be symmetric block cipher because that's efficient in computers, bitwise operations, right? Essentially, the key is always a little bit bigger, 128-bit data and 128 to 256-bit keys. We will do an example at some point later in the semester where you encrypt something with keys of like 2046, 2048, and you will see literally that it's going to slow down significantly. So, there's a trade-off there. And they selected around 2001, Richendell, so that's probably the authors of, that proposed the work. Okay. All right, so as you know, we've been talking about Bob and Alice. So, Bob sends a message, Alice somewhere else in the world, and Zelda is going to be the one that intercepts. So I'll use Bob and Alice a lot more because you guys have to do your homework assignments with a partner, right? Because it's going to get much more complicated just because of so many things that you're going to have. So now you're going to have each of you will have three keys in your computer instead of just one key, right? And that's kind of what I'm going to talk about today. So you need to know who's Bob, who's Alice, and also that something is not intercepted by Zelda. All right, so here we're going to talk a little bit about properties of symmetric encryption, kind of to summarize this. So the pros, confidentiality. So Zelda cannot access the message without knowing the key, right? So that's the idea. Authentication, only whoever knows the key can participate in the communication, right? You can see that there. Integrity, if the message C is modified, it will decrypt to gibberish, right? We've actually tested this. So I guess it depends on the algorithm a little bit. Here's the cons, though, of symmetric encryption. So this is kind of the motivation. Key distribution is critical and requires out-of-band communication, right? So you guys understand this. So you have to meet at a coffee shop and exchange the key. If key is compromised, Zelda can impersonate both Bob and Alice. So there's no way of authenticating, right? Once you have the key, you can pretend. You can be somewhere in the world and just pretend to be Bob and Alice when you're not. It cannot be used to prove that the message was sent by specifically one of the involved parties. The non-repudiation thing. So this actually becomes more important now. So let's say that two people enter into a contract and then somebody wants to back out of the contract, right? There's got to be a way to say, no, but you signed it. And I have proof right here, right? So that's one of the and this is all done digitally, of course. So we're going to talk about these signatures, certificate authorities also. And so that's coming up. But anyway, this is the problems, right? Okay, so some practical security issues. So typically symmetric encryption is applied to a unit of data larger than a single 64-bit block or 128 block. We've talked about ECB. Remember the difference between ECB and CBC. So electronic codebook is the simplest approach to multi-block encryption, right? And we've seen several examples of this. Each block of plain text is encrypted using the same key, but cryptanalysts may be able to exploit regularities in the plain text, right? So we saw that. That's the image example. Also remember the modes of operation as ECB and CBC, for instance, so alternative techniques developed to increase the security of symmetric block encryption for larger sequences. So this is ECB, right? So then an image, and you guys can make out, right, that at least the hair, right? There's some kind of a pattern there, okay? And so obviously that's not secure because it doesn't meet the definition of Claude Shannon. Remember, I gave you that equation. It's going to be on the exam for sure. So, it doesn't meet the condition because you can tell something about the original message from the cipher itself, okay? All right, so block ciphers and stream encryption. We also talked about this one, right? So we have a block cipher, such as electronic codebook, plain text, and key gets XORed to produce cipher 1, and then cipher 1 and key get XORed to produce the plain text back, right? On the blockwise basis. Stream encryption on the other one is on a per byte basis, right? That's essentially the key, right? So stream cipher were produced, and also we have, remember, a pseudo-random byte generator, right? PSG, okay? And so pseudo-random generator is a function that we talked about, takes in a seed, and then it just starts producing, bytes, key bytes, you can call them, in a sequence, and then you're going to XOR those with the bytes of your plain text message. So you can see that there we have the plain byte. So the plain byte goes into the stream, and then the pseudo-random generator produces the key byte. Those are going to get XORed. That gets sent out into the internet, and then the process on the other end, using the same key, the pseudo-random generator generates the key byte, it receives the cipher byte, XORs those two to produce the plain byte. Okay, so remember that's also the difference between stream ciphers and block ciphers. Okay, block and stream ciphers processes the input one block of elements at a time, produces an output block for each input, can reuse keys. The stream cipher processes the input elements continuously, produces output one element at a time, such as 1 byte at a time. So the primary advantage is that they are almost always faster and use far less code. And you can see encrypts plain text 1 byte at a time. Okay. Message authentication, we talked about this one. This relates to what pillar? Message authentication, max, hash, integrity. Yes, don't forget those things, right? So that's pretty important. Protects against active attack, verifies received message is authentic, right? Now, does it care about confidentiality? Not necessarily, right? The key pillar is integrity. However, I may ask you to do something where you achieve both integrity and confidentiality at the same time. I think I did that in one of the homework assignments, right? So you may have something like that on the exam. Okay. So the contents have not been altered from an authentic source and timely and a correct sequence. Yeah, only sender and receiver share a key. So we saw that also in hash algorithms, that we can have functions that use a key. Here's an example, a nice little graphic example. I think it's pretty interesting. So you have a message, right? And you have a MAC algorithm, the hashing algorithm, such as hash XOR, that produces the hash value. You send the plain text and the hash value together. You did that in one of the assignments. And then on the other end, this is going to be received. You just take the plain text, run it through the same algorithm to produce a hash, and then you compare both of them, right? So that last verification is just a true or false. Do those two match? If they do match, that's it. And that's actually a great mechanism that we will see later on all semester. So, in a previous slide, it said something like, we're going to check until if you're doing a brute force analysis, we're going to check all the decryptions until it doesn't produce gibberish, right? Think about that, though. That's like impossible. Who's going to read all these messages until one of them is not gibberish, right? Instead, what you want to do is a situation like this, where you decrypt something to a value that you compare to another value, and boom, you got things to work. So as we start making more complicated encryptions, like certificate authority signatures, for instance, they will use the hash as part of it. Okay, so that we can easily just check that things match. Okay, but we'll see that a little later. Just keep that in mind for now. Sam, question. What was the definition of a hash algorithm? Yes.
Mapping something of variable length to something of fixed length.
Yes, exactly. Exactly right. So, and we saw that in an example, right? We encrypted, a paragraph, I believe. So message of data block, you break it into blocks of L bits, and that function will map to fixed length. That's always fixed length. And so that's the approach, essentially. So you can see the function there. Lowercase h is equal to uppercase h. Uppercase h is the function, and m is the input to it. So that is the hash. All right, hash function requirements can be applied to a block of data of any size. We know that. Produces a fixed length output. The function is relatively easy to compute for any given x. Just a series of XORs. But it is computationally infeasible, or next to impossible, to go from a hash value back to the original text. It doesn't work that way, right? This is one that doesn't work in reverse, right? We just always have to do it forwards and compare. So security of hash functions, there are two approaches to attacking a secure hash. Cryptanalysis again, exploit logical weaknesses in the algorithm. Yeah, that's hard. Brute force attack. We know this one. Strength of hash function depends solely on the length of the hash code produced by the algorithm. And then SHA-256 is the most widely used hash algorithm. Okay. Applications. Hash is actually very versatile. I think I've mentioned this before. It's like RSA is like elegant. DES and AES are very useful. Hash has a lot of applications, even outside of cryptography. So I don't know if you guys know, but your antivirus scanner, right? Your static antivirus scanner is essentially looking at hashes. Okay, so we'll do that at the end of the semester when we look at applications. That will be one of the use cases that we will look at. Actually, for those of you that know what a denial of service attack, you'd be surprised maybe that one of the defenses in an operating system is based on hashes. So you can use hashes, such as this one, to protect against denial of service attacks, and we will look at that as well a little later in the semester. And of course, the big example, blockchain, right? Crypto is actually based on a lot of these ideas, including hash values, the whole mining thing and all that, right? You'd be surprised it's just computing hash values of a certain complexity. So that's the idea. You produce a hash, and that hash has to meet a certain complexity level. And if it doesn't meet it, then you produce another one. So mining means what? Doing that multiple times until you hit that one that has that security, and boom, it's accepted in the blockchain. You see that? But what does that take? It takes like a GPU or something, like a powerful computer that can efficiently do that and really fast. So that's mining, right? But we'll talk about all that a little bit later as well. All right. Yeah, and some other applications. Oh, passwords. Yeah. So also the passwords get hashed, right? And so on. Intrusion detection. So many applications. Cryptography is not just for like securing and codes and things like that. Many applications throughout computing. All right, that's great. So now I'm going to motivate a little bit towards RSA, right? So as you guys know, I'm kind of wrapping up this main third of the class. I will, of course, still have a few loose ends that we're going to cover later in the semester, but we are now switching to RSA, after the exam. So limitations of symmetric secret key encryption, right? So this is the block cipher, right? So you should be aware. So what are the limitations? So it's pretty good to achieve confidentiality. It's actually the preferred method, right? So it's not like we're going to replace it. We're going to AES, all this would still be used to encrypt that movie that you're downloading on your Netflix, for instance. So the fundamental limitation of symmetric secret key encryption is, how do two parties agree on the key? You've been struggling with this problem all semester, right? So how do you do that? So in order for Alice and Bob to communicate securely, they need to agree on a secret key. In order to agree on a secret key, they need to be able to communicate securely. So it's a chicken and egg problem, right? So how do we solve it? So today we're just going to briefly look at this. So this problem is especially common in the digital age, right? We constantly end up at websites with whom we decide we want to communicate securely, like online stores, but with whom there is not really an option to communicate offline to agree on some kind of a secret key. So that's like if you went to Netflix for the first time to, watch your movies, and Netflix said, okay, come over to the office in Chicago, and we're going to sit down and I'm going to give you your keys, and then you go back to your computer and you're all set to watch your movies, right? So, yeah, so that's the issue. So you instead, what do? You grab your computer, you type Netflix, right? and or whatever website you're going to for the first time, and you get there and all of a sudden you're going to have a key. But how did that happen, right? Without you having to go to a coffee shop. Does that make sense, guys? Yeah. All right. So that's essentially what we're going to look at. So in fact, it's usually all done automatically, browser to browser. And for the browser and server, there's not even a concept of offline. They only exist online, right? So we need to be able to establish secure communication over an insecure channel. Symmetric encryption cannot do this for us. And here we are. The solution is asymmetric encryption. So this is also, you probably have heard of this as the public key encryption, public key infrastructure, PKI, or public and private key scheme or something like that. And that's essentially something that was invented by three people that we will discuss later. We'll go over the math of it is basically algebra. So it's actually like very interesting how simple it is in essence. The math is high school level math, right? Algebra. And so it's very, very interesting to understand. But they basically created an idea, a very interesting idea. So in asymmetric or public key cryptography, both communicating parties, i.e. Bob and Alice, have two keys of their own. Okay? Just to be clear, that's 4 keys total. Right? So this is what I was saying. So now, you've been doing your assignments with a partner. You had like a plain text and a cipher, and then you had what? You had a secret key, and then the algorithms. Now, each of you is going to have your own public and private key that you have to learn when you need to use it. Plus, there will be a secret key, plus the algorithm. Okay. Now, RSA is not for encrypting the message. This is something that should be key. RSA is actually slower than AES or DES, right? Much slower, like significantly slower. It's also not designed for really big things. Do you guys see that? It's not designed for taking a whole, even if you broke that movie into chunks and then use RSA to encrypt it, that would be bad. You could break RSA that way. So it's not meant for that. RSA is meant for key exchange and for encrypting small things, like a key of 128 bits. I mean, it could be like 20,000 bits, but it's still relatively small compared to a movie that lasts 3 hours, for instance, right? So that's essentially the key thing. All right, so only for key exchange, RSA. But without it, there would be no internet. Without it, you'd have to go to, like I said, Chicago and get the keys and things like that. It's the only secure way of doing this. So now, each of you, I'll show you via OpenSSL, via PyCryptoDome. I'll show you guys how to create the public and private keys. The key is that the key idea is that when you create a public key, you create the corresponding pair, right? So they're tied together. So a public and a private key, right? One, you generate one, and then from that one you generate the other one. So they can actually work together. So for instance, something that's encrypted with one public key can only be decrypted with a corresponding private key, and vice versa, right? We'll see that too, all right? So each party has their own public key, this is the other thing also. You create 2 keys. Each of you, right, creates 2 keys, public and private key. The public key is public. That means that you can create your own X account or whatever and put your public key right there, and you tell anyone, hey, if you want to send us a secure message, please use my public key. Do you guys see that? Everyone can view it, access it, but you also have a matching private key, and that you should keep secret. You don't share that with anyone, and that's, it's going to be in your computer or something. So yeah, so each party has their own public key, which they share with the world, and their own private key, which they, keep private. In more than that, they want to keep it as a very closely guarded secret. So that's, of course, when we try to break RSA, what you want is to get that private key, right? Somehow. How do I figure out how to break and get that private key? Because then you can do just about anything. So that's, for us to understand how that works, we first need to look at the algorithm, the math of it, and we'll play with that later after the exam. All right. So asymmetric public key encryption, the magic, which is, I should say, it's math. The magic of public key cryptography is that a message encrypted with the public key can only be decrypted with the private key. Okay, so that's really important. So let's think now. You have to, right? Think in terms of Bob and Alice. So Alice will encrypt her message with Bob's public key. That's the other thing, right? So she's not using her public key. She's going to use the recipient's public key. So you have to remember that requirement. And you have to know if you want confidentiality or authentication, because that's also important here. So we'll see that there. But let's consider this scenario. Alice will encrypt her message with Bob's public key. And even though Zelda knows that she used Bob's public key, and even though Zelda knows Bob's actual public key, she is unable to decrypt the message. Only Bob, using his private key, and I should have said private there, using his private key can decrypt the message because it's the matching. The message was encrypted with Bob's public key, so only Bob's private key can decrypt it, right? So that's the key idea. Got it? Any questions on that, guys? All right, let's take a look at a diagram, essentially. So this is for confidentiality, right? You're trying to achieve confidentiality, not of the message, remember, but of the key. So what are you exchanging when you're using this? You're going to be using AES or DES for the actual confidentiality. Do you see that? But you need to send that key. Alice wants to communicate with Bob, so she needs to send that key. And so to send that key securely, the problem that you had since the very first week of the semester is that you needed to encrypt that key, the AES key, and this is the way to do it. So Alice will create a private and a public key, and Bob also will create a public and a private key. And assume, like in the first picture, Alice is on the moon, Bob is on Earth, right? So they're really far away. But Alice has a website and Bob has a website, and they place their public key there. That's it. So then Alice wants to send the AES key to Bob. So what is she going to do? She goes online, she downloads Bob's public key, which anyone on Earth can download that, right? But Zelda also. So then Alice has a plain text message, which is going to be the AES key, let's assume. She's going to take Bob's public key and is going to use that to encrypt and produce the ciphertext. At that point, the message has been encrypted with RSA, right? Or there's another one, I should say, called elliptic curves. So we'll take a look at that one too. That's even more advanced math. It's based on like geometry, but they're essentially kind of the same idea. There's just where you're getting your values from changes a little bit. So RSA uses prime numbers, and then elliptic curves uses more of this geometric elliptic curve. So anyway, so you have the plain text. Alice uses Bob's public key. She encrypts the message with RSA, produces a ciphertext, sends the ciphertext across the insecure internet. Zelda is snooping, but if she doesn't have Bob's private key, she cannot decrypt the message. Then on the receiving end, Bob receives the ciphertext, and he's going to use his private key to decrypt it and obtain the plain text message. At this point, what you have accomplished is key establishment. Okay? And now they both agreed that they were going to use AES, CBC, for instance. So now they just proceed to exchange their secure messages via AES CBC. So this is what happens when you go to, Amazon or something like that. The first thing is you do key establishment like that. Once Amazon has the symmetric key and you have the symmetric key, then you start using a second algorithm, AES, to actually send the data, your credit card information and all that stuff. And this happens actually, you'd be surprised, but this happens like every minute there's a new key, right? And that makes sense, right? Because it's more secure. Like the idea is, what if you were using that key for 3 months and if you're going to your Bank of America or something, right? And the policy was to, oh yeah, just give them a key once for 3 months. Well, the problem with that is somebody's going to try to break it and steal your money, right? So a lot of these websites, it's like per transaction, and once that's over, it's a new one, a new key, and so on. And that just adds even more security. It's just digital data, so it's not like it's expensive or anything. It takes a little bit of processing, obviously. So yeah, consider it. Got it, guys? Does this make sense? Yeah, go ahead. If you have questions, please ask. Yeah. Yes. Well, actually, that's a good point. So I meant the symmetric key. That's a good question, actually. I appreciate that. Not the public and private key. I meant the AES key. Because actually, we'll see this later on with certificate authorities. Let me ask you this question. So let's say you, right? What's your name?
Ruben.
Ruben. All right. So Ruben, and Bob is Amazon. Okay. So Ruben, you want to make a purchase from Amazon, right? You find a website that says that they're Amazon, but how do you believe it? And they say, this is my public key. How can you trust that that's them? Do you see that? So actually then, this is the part of the internet that does have to happen at a coffee shop, right? So there is a part where Amazon at some point, we'll see this later in the semester, but it's because you asked the question, so it's actually pretty good. Amazon has to go to someone's office physically and say, this is my public key, can you sign it? So there's going to be an additional, what is called a certificate, right, associated with the public key. So that's why this cannot be constantly, like every minute, because for a while, every so often, they'll generate a new key for sure, but they'll go somewhere and have their key signed. So that one company that does this is VeriSign, if you've ever heard of them. So and that's the one part of the internet where you have to meet in person, and it requires longer duration. But the other part, and also then you're asking, so how do you get the public and private key on your end? It's the browser that does it for you. Okay, so the key then is you get the public key from something like Amazon that has been there for a while because it has a certificate associated with it. So when you download that public key to your browser, the first thing the browser does is it checks that certificate. Is this VeriSign's certificate? And they can do that. Do you guys see that? So that one has to be more permanent. But then after that, you can issue symmetric keys for the confidentiality part every minute or every 10 minutes, however you want to do it. Got it?
Yeah.
Yeah. Perfect. Good question. That was actually a good question. Guys, do you have any other questions or thoughts? Okay, so that's kind of the review. And just leading to RSA. I think this is as far as I'm going to get with RSA this week. All right, I think I have this is the last slide, I believe. Yeah. And then I believe there's another set of slides, but I may be wrong. Second. And then we'll just go back to DES. Remember, we still need to finish the DES algorithm. All right, so we covered this one. covered this one. Yeah, all right. So I thought I had two, but I guess there's only one because we did do the first one. This is the one that has the pillars. All right. So that is the slides and kind of the review. What we have left today is to finish up the DES algorithm. So I'm going to go to the whiteboard. Kind of we left off at the Feistel network, if you remember. So we just have to get to the end of that. And then there's, like the lab for this week. All right. So we'll go over that as well. Okay. So let me actually, yeah, so this is the Feistel network. And then there's the homework that's due Thursday, right? This one, due Thursday, CBC. And then exam one. And then we will pick up with RSA probably on Thursday. Okay. All right, so let me end this video here and I'll create a new one.